Welcome. Today I'll walk you through the process of obfuscation using lookup table. For this process, we'll be using the graphical user interface, which is built for the Linux operating system and requires the Synopsys tool for its working. This graphical user interface automates most of the underlying process and allow the user to go back and forth during the process. With just a few clicks of a button, the user can obfuscate any netlist with ease. This tool has 5 different tabs which we will explore one by one. The first step of obfuscation is synthesis, which is an essential step, as in this stage we will convert the Verilog or VHDL file to the synthesizer netlist using the GTEC library. If the provided netlist is already synthesized with another library, the tool also accepts the target library for converting the synthesized netlist to the GTEC. This step converts any design to the common GTEC library and thus doesn't require user to acquire additional library. In today's example, we will use the S38584 benchmark for the demonstration. This benchmark is a sequential benchmark and is obtained from the ISCA 89 benchmark suite. The top module is S38584 and the clock name is CK. Clicking on the Synthesize button opens up a pop-up window which shows the synthesis process using Synopsys Design Compiler. Once this process is successful, we get another pop-up which gives us information on where the files are saved, and the same information can also be found in the terminal pop-up window. Moving on, the second tab allows the user to find the gates for replacement. We use the synthesized file from part 1 and fill in the required information. In this example, we'll obfuscate 2 gates with lookup table of size 2. This section will allow the user to control size of the lookup table, number of gates, and the replacement strategy for finding the gates for replacement. This opens the user to many powerful opportunities for obfuscating a design. The pop-up window here gives us information on the selected instances for the obfuscation. In the part 3 of the process, we can test the obfuscation using the SAT attack. The SAT attack is already bundled with this tool, and the tool converts the Verilog file to the bench file which are supported by the SAT attack swiftly. To run the SAT attack, we just need to provide the Oracle file along with the obfuscated file generated from part 2. We can see that SAT solver process in the pop-up window, and we can see that the SAT attack can reverse engineer this small obfuscation within just few seconds. If we are satisfied with this SAT solver performance, we can move on to the next step of obfuscation. This is another required step, and we use the file which is synthesized from step 1 and we fill in the required information. This step also requires the config file which is generated in step 2. In case the user wants to specify the gates for obfuscation manually, few edits to the config file can allow the user to do so. Clicking on the obfuscate file takes the Verilog file along with the config file to generate the final obfuscated file in Verilog format. The final section of the tool is designed to perform the SAT attack post-obfuscation process. This allows the user to convert the obfuscated netlist to the bench format for the SAT attack. The tool provides information where the files are saved upon successful completion of the process. The converted files can then be used to run the SAT attack just like we did in section 3. This process summarizes the lookup table based obfuscation toolkit. Hope you enjoyed it. Thank you.